Check one. Can you all hear me? Is it loud and clear? You can put on the chat. Once you're joining through YouTube, is it clear? Can you all hear? Right, one more sound check. Can you all hear me loud and clearly? One more sound check. Can you all hear me loud and clearly? Right. Good evening, everybody. Welcome to another session of Helpline. So, like I told you, we'll complete some good questions that are there. This is the 2010 A-level question which I told you all to do. 2010 A-level question. Okay? 2010 A-level question. And 2014 A-level question. 2010 A-level question. This is your mechanics question. Mechanics question. Right. Let me read the question carefully. Yeah? Let me read the question carefully. A uniform rod AB of square cross section, mass M and length L, rests on a horizontal frictionless surface as shown in the figure. Moment of inertia of the rod about an axis perpendicular to the surface, passing through the center of gravity capital G, is I. So you have a rod like this. You have a rod like this. Center of gravity is there. Center of gravity is there. Length of the rod is there, L. Length of the rod is there, L. Okay, right. The rod is struck by a ball of mass M traveling along the surface without spinning with a velocity V perpendicular to the rod. With a velocity V perpendicular to the rod. The motion of the rod due to the impact of the ball can be studied in terms of linear motion of the center of gravity and rotational motion of the center of gravity. Right. First consider the linear motion of the rod that occurs due to the impact of the ball. Right. Have a look. Now the mass of this is capital M. The mass of the ball that is traveling is simple M. Simple M is traveling with a velocity V. Simple M is traveling with a velocity. Right. A Roman 1. Part A Roman 1. A Roman 1. Have a look. Write down an expression for the linear momentum of the ball before the impact. So looking at this, you can easily say linear momentum is mass into velocity. So M times V. Simple M times V. So not a difficult question. Simple MV. Roman 2. Consider only linear motion. Consider only linear motion of the rod. Obtain an expression for the velocity of the rod after the impact. After the impact. So this is before the impact. Before the impact. They are telling you after the impact, find the linear velocity. Right. So here you have center of gravity. At the center of gravity, there will be a velocity. And the ball will rebound in the opposite direction. They have told you in the question itself, the ball is rebounding in the opposite direction with the same velocity. The same speed, ball is rebounding in the opposite direction. Right. So this is after. This part is after. So now you can write the equation, no? Total initial linear momentum equals total final linear momentum. So if I write it here, total initial linear momentum equals total final linear momentum. So here if I write it, I'll use this space. Roman 2. I'll write short form, but you must write in full words. Huh? Total initial linear momentum equals total final linear momentum. So I'm saving space like this, but you must write in full words. Okay. Right. So I'll write the direction there, put the direction there. Okay. Initial linear momentum, mass into velocity. Please put the direction. Final linear momentum, we can do it like this also. Write the equation, put the direction there. Final linear momentum, mv in the opposite direction. Capital M, let's say v1, otherwise you'll confuse with the velocities, v1. That will be in the forward direction. Bring all vectors in the same direction. Bring all vectors in the same direction. Capital M V1. Simplified. 2mv. Capital M V1. V1 equals 2 simple MV over capital M. 2 simple MV over capital M. So there you go. That's the velocity of the rod. If you want, you can define terms. You can say V1 is velocity of the rod. Velocity of the rod. So what have we done? We have applied law of conservation of linear momentum and then found the velocity of the rod. So if you want, carefully write it down quickly. Write it down quickly. Right. Okay, no? Now what? Second part. Now consider the rotational motion of the rod about its center of gravity. Now we consider the rotational motion of the rod. Now we consider part B, rotational motion of the rod. So here you have the rod. Here you have the center of gravity. Here you have the rod. There you have the center of gravity. Ball is striking a distance x. A distance x. This is before collision. Before collision. And here I can draw after collision. Here I can draw after collision. Here it's going to rebound in the opposite direction. Distance x. And this will create a angular velocity rotation. Omega. Okay. These after. Okay. These after. Right. Read carefully. Yeah? Now consider the rotation motion of the rod around its center of gravity. If the ball strikes the rod at a distance x from the center of gravity, write an expression for the angular momentum of the ball. So what's the definition? Angular momentum is defined as moment of linear momentum. Moment of linear momentum above the axis of rotation. So moment of linear momentum above the axis of rotation is linear momentum into perpendicular distance x, mvx. Is all done. Huh? Moment of linear momentum is mv times x. mv times x. Right. Roman number 2. Roman number 2. What are they asking? Consider only the rotational motion of the rod. Obtain an expression for the angular momentum omega. So we can apply total initial angular momentum. Please write in full words. Huh? Total initial angular momentum equals total final angular momentum of the system. Right. Now we must use the direction. Moment of linear momentum, right hand rule. R times mv in the paper. So mvx you can use your right hand rule, which I taught you all, into the paper. Here, x times mv opposite out of the paper. After mvx out of the paper plus rotation here into the paper. Here, rotation into the paper. Right hand rotation into the paper. I omega into the paper. So please remember, when you are applying law of conservation of angular momentum, you must think about the direction. Direction is important. Direction is important. Now bring all vectors in the same direction. mvx into the paper. Into the paper. If I bring this into the paper, it becomes what? Minus. Into the paper is minus. Plus I omega into the paper. Now all are in the same direction. All are in the same direction. You can rearrange it. 2mvx equals I omega. Omega is equal to 2mvx divided by I. Omega is equal to 2mvx divided by I. Omega is 2mvx divided by I. Okay, no? So don't forget, when you are applying angular momentum, think about the right hand rule. Find the direction and please mark the direction. Very important. This is your level of understanding. Very important when it comes to the basic progression. Okay. Write down carefully the ones who need it. Is it clear? Any doubts? You can put in the chat if you have any doubts. Okay. Right. Now what they're asking you? Part C. Now what are they asking you? Part C. Part C, they're asking you, using the expression obtained in part B, using whatever you found in part B is here. Whatever you found in part B, they're asking you, write down a relationship for the velocity v dash at the end A of the rod. So now don't forget, rod is rotating about the center of gravity. Rod is rotating about the center of gravity. End A of the rod, there is a tangential velocity v dash. In A of the rod, there is a tangential velocity v dash. So we can find v dash. V dash is equal to r omega. R is the length, L over 2. L over 2 times omega. So v dash is L over 2 times omega. Omega we have found earlier. 2mvx divided by I. 2mvx divided by I. 2 cancel off. mvx L divided by I. There you go, v dash. There you go, v dash. Are the directions of v and v dash are the same? I'll mark it here. V is the velocity of the rod, no? V is the velocity of the rod. They are given you there in symbols. Yes. V is the velocity of the rod. Even I think here they are given velocity of rod as V. Best to keep it in the same symbol. Same symbol here. Keep it in terms of capital V. If you want, I will mark it in red color or whatever. Capital V. Don't confuse this V and that V. Right. Okay. So what can you say about V and V dash? Of course, they are in opposite directions. V and V dash are in opposite directions. V and V dash are in opposite directions. Okay. Right. Then what? For a certain value XS. Interesting question. Huh? For a certain value XS, for X, end A of the rod remains at rest. How can the end A of the rod remains at rest? Remember, when you're traveling with linear velocity, every single point will have the same velocity. When this rod is traveling forward, if this pen is traveling forward, every single point on the rod is traveling with the same velocity. So something that you all might not realize, I'll draw it here and show. Every single point on the rod is traveling with the same velocity. Every single point is traveling with the same velocity. And now because of the rotation, don't forget we have a V dash also. We have a V dash also at point A. So they're asking you a very interesting question. For end A to remain at rest, think and tell me now, logically. For end A to remain at rest, what should happen? V and V dash both should be same. If V and V dash both are same, what happens? End A is at rest. So simple. So remember, when a rod is going forward, if I take this pen in the forward direction, from the top to the bottom, every single point is going with the same velocity. So for end A to be at rest, for end A to be at rest, V dash equals V, don't forget. V dash equals V. What is V dash? Do the substitution. Simple MVXL divided by I. Capital V. What is capital V? Capital V we have found earlier, 2mv over m. 2mv over m, 2 simple mv over capital M. There you go. Now simplify this. Simple m, v cancel off, simple m, v cancel off. And now you can say this distance here is x, xs. Here I can write xs equals 2I divided by capital ML. 2I divided by capital ML. Remember, even in a cricket bat, there is something called in the blade, something called a sweet spot. When the ball hits the sweet spot, what happens is there is less force or effort acting on your hands. Nicely, the ball will travel. So this in a tennis racket also, there is a certain place where the ball strikes. There is a certain place where the ball will strike. If it strikes there at a distance xs, at the bottom where you're holding it, let's say you're holding the bat at the bottom, the grip. At the grip, when it strikes, you won't feel sudden forces. That there is no movement of the grip. So this call especially is known as the sweet spot. When the ball strikes the sweet spot, even tennis racket same. When you use the tennis racket, when the ball strikes the sweet spot, what happens is there is less force acting on the tennis racket grip. So when there is lesser force acting on the grip, it's easy for the player. Yeah, easier for the player. So this location, we have actually found the location of the sweet spot. Yeah, they actually found the location of the sweet spot, right? So part D, Roman 3 is there. Yeah, Roman 3 is there. Part D. Part D. Sorry. Part D. Part D. The moment of inertia of the rod is given as 1 over 12 ml squared. If L is 0.6, find the value of XS. So XS equals, we already found it earlier, 2I divided by ml, 2I divided by ml mass into length, 2 ml moment of inertia 1 over 12 ml square. Cancel off, LL cancel off, L over 6. 0.6 divided by 6, 0.1 meter or 10 centimeters from the center of gravity. There you go. That is where your sweet spot is. Right. Consider a player holding the tennis racket. So here you have the tennis racket. Here you have the tennis racket. A player is holding the tennis racket. So he's holding here. What happens if X is, let's say, center of gravity is somewhere there. Let's say center of gravity is somewhere there. If the ball strikes somewhere higher, the blade will come forward. No? So it's going to push, this will turn this way. So it's going to push your hand that direction. So when X is larger than XS, the racket is going to push the forward. It will push your hand in that direction. This will bend. The racket will bend in that direction. When the racket bends in that direction, it's going to push your hand in that direction. Okay. Next one. I'll draw the racket again. Here you go. Now X is smaller than XS, shorter distance. Now the racket is going to bend in the opposite direction. If it's going to bend in the opposite direction, there will be a force in that direction. There will be a force in the opposite direction. So there you go. So here strikes more, the blade will turn this way. So force in that direction. Strike shorter distance, this will go in the opposite direction. You push your hand in that direction. Okay, no? That's all they're asking you. So it's a very good question. This question considers linear law of conservation of linear momentum as well as law of conservation of angular momentum. If I do a small recap, have a look. Ball is traveling, colliding and rebounding. Once it collides and rebounds, if I consider only the linear motion, the rod is going to have a velocity capital V. So total initial linear momentum equals total final linear momentum. Don't forget, rebounding direction opposite. You can find the velocity of the rod. The velocity at the center of gravity of the rod. Next, the ball comes and rebounds. Now think only about the rotational motion. If you think about the rotational motion, you can apply law of conservation of angular momentum. If you apply law of conservation of angular momentum, you can find omega. Okay? You can easily find omega. Omega is 2mbx divided by I, but important part is this. You're applying the right hand rule. RMV inwards, RMV outwards. Here omega inwards, which we learned in theory class and all. Perfect. So here now direction has changed. Bring everything in the same direction. Simplify, you get your answer. Simplify, get your answer. What else? You have a rod. There's a linear velocity there. There's a tangential velocity backwards. You can find that tangential velocity. But something that you should know is, when a rod is trying to go forwards, every single point on the rod will also try to go in the same direction. That means every single point on the rod will have the same velocity. Every single point on the rod will have the same velocity. If you take point A, there is V and B dash. If A is at rest, that's the condition. For A to be at rest, B and B dash should be equal to each other. Simplify it, we can get excess. This is a very important point. What do you call this point? Sweet spot. When the ball strikes this location, the bottom of the grip or the bottom place where you hold the racket does not move. When the bottom of the racket does not move, your full power will go to the shot. Same way in the cricket bat toss. If the ball strikes a sweet spot, your whole energy is transferred to the ball, not to the movement of the bat. So striking the ball at the sweet spot, check and see. A person who perfectly plays with the sweet spot, Sri Lankan, of course, Kumar Sangakkara, Mahela, when they play the cover drive or the off drive or the on drive. Ball strikes the bat, and then those days there was a perfect player called Mavan Atabattu. When he strikes the ball, it stays. I mean, there is less effort. Now, Sanat Jayasuriya, the fellow has to have back the ball. No, he has to hit the ball. Full power, hand-eye coordination, power. Tisara Pereira, hand-eye coordination, power. But there were players who are much more. I mean, you won't even. It's nice. It's very nice to see them. Gracefully, they score fours, sixers, etc. So one of them was the ball. Make sure the ball strikes the bat at the correct location. Once the ball strikes the bat at the correct location, there is less force acting on your hands, which means now majority of your power will be transferred to the ball. Same way in tennis. Now, there was a player. Now, of course, you all know Djokovic. You all know what you call Rafa Nadal, Federer, etc. No? Those days, there was a player called Pete Sampras. Pete Sampras used to play the backhand, just like Federer, okay? Backhand player. And he was one player who had less number of injuries, just like Federer. Less injuries. That's because once you strike the ball, the ball strikes at the sweet spot, there'll be less forces acting at the place where you hold. Less forces acting in the place where you hold means less injuries. More power is transferred to the ball. Yeah. More power is transferred to the ball. Now here, when the ball strikes beyond the sweet spot, the racket will turn in that direction. So there's a force on your hand in that direction. If the ball strikes below, the racket will turn in the opposite direction. So the push on your hand is in the forward direction. Okay, no? Push on the hand is in the forward direction. I hope you understood this question. It's a very good question. You can ask any questions in the chat. Quickly put it. I'll give about a minute and then we can quickly go to the next question. Any doubts? Put on the chat. Yeah, any doubts? Okay. Right. Perfect. Next is 2014 A-level question. 2014 A-level question. 2014 A-level question. Read the question carefully. When a person is changing steps while walking, at one instant, the entire body weight of the person is borne only by a single leg. So when his leg is on top, you can see figure number 1. Leg is slightly on top like this. So one leg is there. The other leg is like this. The total weight is borne by one leg. Total weight is borne by one leg. Okay. Front view of the relevant bone structure of this leg is shown in the figure. Front view is shown in the figure. All the forces acting in figure 3 and the weight of the body are acting on one leg plane. Frictional force between the leg and the ground is negligible for this situation. So they have given you certain symbols that you have to use. Fm, resultant force acting on the leg by a group of muscles M. Fs, force acting on the hip socket on the leg. WL, weight of the leg. R, reaction force acting on the leg by the ground. So the first question, part A, Roman number 1. Part A, Roman number 1. Read the question. If the weight of the person is W, express reaction in terms of weight. So I hope you're smart enough to look at this. RW. So what's your answer? Reaction equals W. Because you are doing for figure 1, figure 2 situation. Figure 1, figure 2 situation means reaction balances the weight. Simple. Reaction balances the weight. Right. Roman number 2. Roman number 2. Right. Generally, WL, weight of the leg, is 0.2 W. That means 0.2 times the weight of the person. By taking moments around point P, find a relationship between Fs, theta S and W. So I'll look at figure number 3. Yeah? Figure number 3, they have drawn like this. Figure number 3, they have drawn like this. Here, point P pivot. Point P pivot. Here you go. What are the forces acting? Forces acting. Here you have Fs. Angle 72, no? Angle 72 degrees. Here you have Fs is here. Fm is here. Fm is there. Here this angle is theta S. Okay. Theta S. They are marking and giving here. Weight of the leg is there. Reaction force is acting here. Reaction force. The gap between reaction force and this, they have given 18 centimeters. Be careful. Take time to carefully mark the lengths. The separation here is 8 centimeters. And the separation here is 10 centimeters. That means perpendicular distance to the line of action is 10 centimeters. Right. Take components. About P means Fm won't come, don't worry. Fs cos theta S is there. Fs sin theta S is there. Cos theta S is passing through the pivot, so no moment. Sin theta S will give you moment. Right. Equilibrium condition, clockwise moments about P equal anti-clockwise moments about P. Please write in words first. Clockwise moment about P equals anti-clockwise moments about P. So if you take clockwise moments, Fs sin theta S perpendicular distance 8 centimeter. If you want, convert to meters, plus weight of the leg multiplied by the perpendicular distance 10 centimeters, convert to meters, equals opposite direction r times 18 centimeters, convert to meters. R times 18 centimeters, convert to meters. So 100 cancel off. Fs sine theta s into 8. Weight of the leg they have given you. Weight of the leg is 0.2 W. 0.2 weight into 10. 100 cancel off. No. 100 cancel off. Huh? Don't forget now R is equal to how much? R is equal to W. W times 80. Carefully simplify. Fs sine theta s times 8 plus 2W equals 18W. 2W equals 18W. The distance there is 18. No? So we have found the basic relationship. 18W found. Simplified. We can take Fs sine theta s times 8 equals 16W. Divide 16 by 8, it's going to be Fs sine theta s equals 2W. 2W. What are they asking you? They are asking you to find the relationship between Fs, theta and W. Okay. This is your relationship. So not difficult. Easily you can find the relationship. Easily you can find the relationship. Right. Once you need it, quickly write it down. Anyway, you can watch it slowly and then figure it out. But very simply, we took the moments. Right. Now, you can take components here. You can take components here if you want. Fm, I will indicate it here easier. Fm cos 72. Fm cos 72 balances Fs cos theta s. Fs cos theta s. They are asking you to find Fm in terms of W. Fm in terms of W. Okay. Fm in terms of W. We can also take this no, vertically. Vertically also you can take. Fm sine 72. Fm sine 72. So I'll write the equations here, easier. Roman 3, yeah. Roman 3. Sum of forces in the upward direction balances sum of forces in the downward direction. Okay. No? Upward direction Fm sine 72 plus normal reaction balances Fs sine theta s plus the weight. Plus the weight. Fm sine 72. Sine 72 is 0.9. Normal reaction, don't forget, is W. Fs sine theta s is 2W. Weight is going to be 0.2 W. Simplify this. Fm 0.9. 2.2 minus 1, 1.2 W. Fm equals 1.2 divided by 0.9 W. 4 over 3 W. That's going to be Fm 1.33 W. You can nicely simplify and get the answer. Easily you can get the answer. Remember, these are all very simple work. Don't think too much. If you carefully read the answers, you will get. There is no way you cannot get it. You will guaranteed get it. Right. Find the value of theta s. Find the value of theta s. So we can take horizontal balancing forces. We can balance the horizontal forces. We can balance the horizontal forces. So we can take these Roman number 4. Sum of forces to the right balances sum of forces to the left. Sum of forces to the right balances to the left. Fm cos 72. Fm cos 72. Fm cos 72. Fs cos theta s. Fs cos theta s. Fm already found. 403 W. Cos 72 is 0.3. Cos 72 is 0.3. And you have Fs cos theta s. Simplify this. Fs cos theta s equals 0.4 W. I'll name this, if you want, equation number 2. Equation number 2. I can name this, if you want, equation number 1. Now equation 1 divided by equation 2. Fs sin theta s divided by Fs cos theta s. That is 2W divided by 0.4 W. 2W divided by 0.4 W. Simplify this. Fs cancel off. W cancel off. Here you have tan theta s. 20 divided by 4 is 5. Tan theta s 5. From this you can find, no, theta s is equal to tan inverse 5. Tan inverse 5 you should be able to find. Tan inverse 5. Tan inverse you will get 78 degrees 41 minutes. 78 degrees 41 minutes to go. 78 degrees 41 minutes already found. Find Fs in terms of W. Find Fs in terms of W. So I can substitute to Roman 5. Substitute to equation 1. Fs sin theta s equals 2W. Only for this calculation, take sin theta s as 1. Fs sin 78 degrees 48 minutes, do the substitution. They are telling you for this, take it as 1. So Fs equals 2W. Okay, no? Fs equals 2W. In the question, they are telling you that. So it's not a difficult question. Take some time. Remember, any question that is explained nicely, long questions, that means they have explained the question nicely. Take time to read and do it. If you don't, your generation anyway, you all don't have patience to read. So that's actually a big drawback. Nothing is instant. There's a process. You follow the process. People who try to do instant, at the end, you'll have a lot of problems. There's a process. Follow the process. Then you have no issue. Otherwise, you will have guaranteed issues. Right. Part B. Part B. Part B. When a person with an injured hip joint, now the fellow is having an injury, is walking, he tends to limp by leaning towards the injured side as he steps on the foot. As a result, the center of gravity of the body shifts to the side of the injured hip joint. Okay. FMX vertically upwards. Free body diagram for the injured leg is shown in figure number 5. And the corresponding forces of FM and FS are indicated by FM dash and FS dash. Right. Now, injured leg. Injured leg. FM dash acting upwards. FM dash is acting upwards. FS dash is acting downwards. Gap between these two is given 7 centimeter. 7 centimeter. Weight is acting there, weight of the leg. Weight of the leg and this, the gap there is 6.25 centimeters. Normal reaction is acting here. Normal reaction is acting there. This gap here is going to be 10 centimeters. That gap there is going to be 10 centimeters. Okay. Right. Find the force Fs dash for the situation in terms of W. In terms of W. So don't forget, normal reaction is actually W. One leg is up, no? Can you see? Figure number 4 is like this. Fellow is like this. One leg. Total weight is acting there. Total weight is acting there. What? Take moments about P. Roman 1. Clockwise moments about P equal anti-clockwise moments about P. So if you take the clockwise moments about P, Fs dash into 7 centimeters. Fs dash into 7 centimeters clockwise. Any more clockwise? Yes. Weight into 6.25. Weight of leg into 6.25 centimeters convert to meters. Anti-clockwise normal reaction 10 centimeters into meters. All these 100 you can cancel off. Think carefully and work now. Fs dash into 7. Weight of leg is given 0.2 times W. 6.25. Normal reaction is W times 10. Fs dash times 7 plus. Don't be in a hurry. Process is you have to calculate. 2 times 5, 12. 3 decimal places 1.25 W. 10 W. Fs dash 7. 10 minus 1.25, 8.75 W. Fs dash is 8.75 W divided by 7. 17 you have 2, 35 you have 5. 1.25 W. 1.25 W. Okay. Roman 2. Calculate the percentage change, percentage reduction in the magnitude of Fs. Earlier, how much was Fs? Fs was 2W. Normal man walking, Fs is 2W. Limping man, 1.25. Percentage reduction. I'll write like this, percentage reduction in Fs. Reduced amount, Fs minus Fs dash divided by initial multiplied by 100. Reduced amount divided by initial multiplied by 100. Reduced amount 2W minus 1.25 W divided by 2W into 100. Simplify this. 0.75 W divided by 2W into 100. WW cancel off 0.375 multiplied by 100. Percentage reduction in the force there is 37.5. So if a man was walking straight, the force on the hip bone will be 2W on the joint. He is limping now. the force reduction or the force reducers to 1.25 W. There's a reduction of 37.5%. 37.5%. Okay. So I think the answers will be correct because there is no way it can go wrong. Perfectly, we have done it. Part C. Part C. Read question carefully. In the process of walking, while one leg rests on the ground, the other leg moves up around the hip joint. So you're walking like this. Imagine your leg is going like this. One leg is stationary, the other leg is going. Stationary, going. Stationary, going. Stationary, going. Like that. Okay. There's oscillation. This motion can be considered as oscillatory motion about the rod, which is freely pivoted, one of the shown in figure 6. So freely pivoted oscillation, as shown in figure number 6. Figure number 6 is at the bottom, bottom of the question. Right. Here the leg is considered as a uniform rod, length L. So now remember, now just like our arms are moving like this, the leg is also around the hip joint. Now if you stand and if you just move your leg like this, like when you're cycling, see you're moving your leg around the hip joint. Okay. If I is the moment of inertia of the rod of the axis of rotation about Q, obtain an expression for the angular acceleration alpha in terms of L, theta, W, L, weight of the leg, and moment of inertia. Indicate is the position in figure number 6. So right. This is your part C, Roman 1. Figure number 6, they have given you here like this. About Q. Here the weight is weight of the leg, no? WL. Am I correct? WL. Exactly half the length L here, theta there. So all of you all know basic work. Extend the line of action. Perpendicular distance there. L over 2 sine theta. That's all. Cos theta, sine theta. So the torque is equal to I alpha. Torque is weight of the leg L over 2 sine theta. Moment of inertia I into alpha. Moment of inertia I into alpha. Okay. They ask obtain a position for alpha. Alpha is weight of the leg L sine theta divided by 2 moment of inertia I. Okay, no? Weight of the leg L sine theta divided by 2 times moment of inertia. Okay. Roman 2. The period of oscillation of the rod T can be obtained by T equal 2 pi theta over alpha. They have given you, so don't panic. They have given you that. And it can be shown that T equals 2 pi 2L over G for the uniform rod. Right. Calculate T. So we are used T equals 2 pi 2L over 3G. This only we must use. T equals 2 pi. Length of the leg is 0.9. 3 times G is 10. Here 2 times pi is 3. 1.8. 1.8 divided by 30. 1.8 divided by 30 square root. Periodic time 6 times square root 0.06. Square root 0.06 is 0.25. 1.5 seconds. Periodic time is 1.5 seconds. Right. So that's good. Roman 3. That's simple, you can see. The most effortless speed walking for a person is the speed where his legs oscillate with the period obtained in C Roman 2. When a person with 0.9 meter long legs is walking, the distance between two successive positions where one leg touches the ground. So I'll draw this. One leg on top. So here, from here, now front leg, back leg behind. This is front leg. Now front leg is here. Front leg, front leg. This distance is 0.9 meters itself. 0.9 meters itself. They are asking the most effortless speed. Actually, this is a very good question. Think. When his leg is rotating one full cycle about the hip bone, time is 1.5, he is going 0.9. So distance divided by time will give you speed. Actually, if we were focusing on biomechanics on our athletes, depending on the length of their leg, their cycle will change. How quickly their legs rotate will change. Depending on that, their maximum speed will change. So if you are going to what you call biomechanics to study our athletes, depending on the length of their legs, we can actually program them to practice so that they are forward spacers. This length is more. So every cycle, the length is more means the speed is also not increasing. So the speed here, if you do the basic calculation, here, speed is distance 0.9, time taken 1.5 meters and seconds. 3 over 5, your answer is 0.6 meters per second. 0.6 meters per second. So imagine, now check and see, especially the ones who are doing long distance running. Every bend, their speed will increase. That means they use their bend to keep their legs closer and increase. Or when you're going far away, when you're taking the 8th lane, corner lane, your legs should be kept at a longer distance. When you're running the corner lane, if your legs are kept at shorter distance, you travel short distances. So that's how you can program running. So you can see when your leg is moving, one cycle, there's a periodic time. Every cycle it moves, you're going forward 0.9. So speed is distance over time. From there, you can find the relationship. Effortless walking speed. Right. So I think you understood this question very well. I'll do a small recap again. Actually, the calculation part is easy for you all. Apply moments, get the relationship. When he's injured, the forces on the hip are vertical. There, of course, the force will change. From there, you can calculate the percentage reduction. The important part comes here. So when his leg is moving in a cycle, he's going forward. When your leg is moving in a cycle, you're going forward. When your leg is moving in a cycle, you're going forward. So every cycle, you're going forward. Every cycle, you're going forward. So you're going forward means 0.9. 0.9 meters in periodic time. From there, it will give you speed. Okay, no? Right. I hope this is very helpful. And I will inform you all about the next 2 questions for next week in your class times. Hopefully, you all do it and they will join for the discussion. Okay. Keep working. Patiently work. Remember, when you patiently work, you will learn a lot about yourself and you will learn the subject well as well. Okay. Take care. Stay at home. Keep working. Believe that always your destiny you can change. Your result you can change. And that is what you need to believe. Take care.